Page 99. Single, double, or triple covalent bonds. We've just drawn structures of covalent molecules with these types of bonds. Let's review briefly. Here are the Lewis symbols of carbon, group 4A, nitrogen, group 5A, oxygen, group 6A. Let's consider oxygen first. Oxygen is a reactive nonmetal. If it's bonded with a metal, it will often take 2 electrons from it and simply form an oxide anion in an ionic compound. But when oxygen is bonded with nonmetals, it generally can't take electrons, and the only way to fill its valence shell is to share 2 electrons, and we've seen that it can form 2 single bonds to fill the valence shell with 8 electrons, or 1 double bond. Now in all cases here, oxygen has 2 bonds and 2 non-bonded pairs of electrons, at least in its covalent compounds. How about nitrogen? Nitrogen is a pretty reactive nonmetal. If it's bonded with a reactive metal, it may be able to take 3 electrons from it, in which case it forms a nitride anion. But when nitrogen is bonded to other nonmetals, it generally can't take electrons, so it has to share to fill the valence shell. We've seen nitrogen can have 3 single bonds, as in the case of ammonia, or it could have a triple bond, as we saw in a nitrogen molecule, or it can even form a double bond and a single bond. We didn't draw this structure, but here's the structure of nitrous acid. In these cases, notice that nitrogen has a non-bonded pair of electrons and 3 bonds on it. What about carbon? Well, carbon wants to form 4 bonds to fill its valence shell. It's not metallic enough that it would ever lose electrons, nor is it non-metallic enough that it could ever take electrons, so generally it forms covalent bonds almost exclusively. We saw that it can form 4 single bonds, like in the case of methane, a double bond and 2 single bonds, as in ethylene. We saw carbon can form 2 double bonds, as in the case of carbon dioxide. And carbon can even form a triple bond and 1 single bond for a total of 4 bonds, as we saw in acetylene or hydrogen cyanide. Note that carbon doesn't have any non-bonded electrons in its structures. Page 110, please. The bottom of the page, I have some important rules about bonding that will stretch you beyond what you probably already know. So these are 3 rules that don't always agree. Rules for drawing Lewis structures, also known as line bond structures. The first rule is the first rule you ever taught when you take chemistry. Valence electrons bond so that all atoms obtain a valence electron configuration like or isoelectronic with the nearest noble gas. That's called the Octet Rule. Well, this rule has a lot of exceptions, so let's move on. In bold is an important rule. Number 2, unpaired valence electrons, that means single unpaired electrons, will always bond, whereas the paired non-bonded electrons sometimes bond. Now in all the structures we've drawn so far, for example, we draw the structure of a water molecule. Here's the Lewis symbol. Bonding with hydrogen. So we're saying that the single unpaired electrons always bond. That's generally going to be true. There are some exceptions we'll talk about later, but they're extremely reactive compounds and not around for too long. Now the non-bonded pairs of electrons, the pairs, may or may not bond. That's what we're talking about now. I want to read it again. Unpaired single valence electrons always bond. The paired valence electrons sometimes bond. Now the third rule and the second rule are much more reliable than the first rule, and they certainly violate it. So please note the third rule with me. Rule number 3, the maximum number of valence electrons an atom can accommodate, and hence the maximum number of bonds that it can form, is limited by the number of available orbitals. So the first period elements are helium and hydrogen. Now they can accommodate a maximum of 2 electrons in their 1s orbital, and that's all they have in the first shell, and so hydrogen can only ever form 1 bond. It's monovalent. It's always terminal in a structure. It's never in the middle. And helium, of course, can't form any bonds because it already has 2 electrons in the valence shell as the atom. There are no known compounds of helium. Second period elements, lithium to fluoride, can accommodate up to 8 electrons in the valence shell, a maximum of 4 bonds. No more, never more than 4. They can only use their 2s and their 2p orbitals. 2s, 2px, 2py, 2pz, 2 electrons per orbital, 4 orbitals, 8 electrons. Maximum, 4 bonds maximum. No exceptions. There are no compounds made from the second period elements that have more than 4 bonds. You say, what about the 3s orbitals? Yes, they're there, there's space, but it's too high in energy. Any bond involving a third shell orbital for a second period element inevitably falls apart. They're just not stable. Never been observed. Third period elements and higher, meaning fourth period, fifth period, sixth period elements, they can use their valence shell s and p and d orbitals, and therefore they can accommodate more than 8 electrons to form more than 4 bonds. So we can violate the octet rule. For any element in the third or fourth or fifth period and so on, they can have more than 8 electrons. They can have more than 4 bonds. Atoms that have more than 4 bonds are said to be hypervalent. Like a hyperactive child runs around super fast, a hypervalent atom can have more than 4 bonds, more than 8 electrons. In fact, some can have up to 7 bonds. Page 103, please. I have a number of formulas that I'm asking you to draw the line bond structures for, and I'm not going to take these up in the video because all the answers for these are drawn out at the end of this chapter, so I commit them to you as homework to do. Make sure that you do them, and just be careful to remember that not all of these are necessarily covalent. Some are ionic, some may be a mixture of covalent and ionic, so just keep that in mind. Let's slide off to the side here. I've asked you to draw the structure of beryllium hydride. Beryllium is in group 2a, so it only has 2 valence electrons. And hydrogen is in group 1a, it only has 1 valence electron, so guess what? This is the structure of beryllium hydride. Let's take a look at an animation of it. So what do you notice about beryllium hydride? How many electrons are in the valence shell of beryllium? Only 4. It has an incomplete octet. How is that possible? This is a real compound. It exists. It's pretty reactive, but it certainly exists. How about we draw the structure of borane Bh3? Boron is in group 3a. It has 3 valence electrons. Hydrogen has 1 valence electron. Boron has an electronegativity of 2.0. Hydrogen is 2.1. So this is definitely a non-polar covalent bond. This is a real compound. There's lots of borane made. It's a very toxic compound, but it's certainly real. How many electrons are in the valence shell of boron? Well, only 6. It has an incomplete octet. Let's take a look at an animation of Bh3. So there's Bh3. It has an incomplete octet. It's a stable compound. Well, I say stable. It's a reactive compound. What's the molecular geometry of that? It's a flat triangle, so it's triangular planar. The point of this exercise was to tell you that there are compounds that have an incomplete octet. They can still be reactive and nonetheless real compounds. These are called subvalent compounds. Subvalent compounds have less than 8 electrons in the valence shell. They typically come from group 2a or 3a, boron and aluminum. It's also possible to have compounds with more than 8 electrons in the valence shell, as we mentioned moments ago, and those are called hypervalent atoms. And atoms that have more than 4 bonds around them are called hypervalent. Let's look at some examples. I'd like to start by having you draw, let's draw PCl3 first. Phosphorus trichloride, or phosphorus trichloride. This is group 5A. Group 7A, 5 plus 7 times 3, 21, and 5 is 26 valence electrons. Electron negativities, please. 2.1, phosphorus is the same as hydrogen, 3.0 for chlorine. So phosphorus will have one pair and 3 unpaired electrons. Remember the rule? The single unpaired electrons always form bonds. The pairs may or may not. In the case of PCl3, what's that going to look like? Chlorine's in group 7A. The difference in electronegativity is 3 minus 2.1 is 0.9. That's polar covalent, so it's going to be shared, not ionic. One there, and one there. It's going to look a lot like ammonia. So this is a fourth pair of electrons. It takes up space. It's going to have the same kind of geometry as ammonia did. Okay, well that's fine. How many electrons are in the valence shell of phosphorus? Well, I see 2, 4, 6, 8. That's fine. It satisfies the octet rule. How about chlorines? They have 8 in the valence shell. But there also is a compound called PCl5, phosphorus pentachloride, for real. What would that look like? Phosphorus with its 5 valence electrons, and we have 5 chlorines. Yikes, where are they going to go? Well, they're going to all be bonded to the phosphorus because it's the least electronegative atom. Okay, so there's 3 chlorines. That takes up all the single unpaired electrons. But remember that paired electrons, they may or may not bond. In the case of PCl5, they're going to have to bond. There are no other electrons for phosphorus to share. So there it is. PCl5. How many electrons have we have in there? Group 5A, group 7A. That's 5 plus 7 times 5 is 35, and 5 is 40 valence electrons. Let's count them up. Bonding electrons, non-bonding electrons, valence electrons. Bonding. There's 5 bonds. That's 10 bonding electrons. We have 5 chlorine atoms, each with 6 non-bonded electrons. That's another 30 for a total of 40 valence electrons, and that works, so that's good. Phosphorus is a hypervalent atom in this case. It has more than 4 bonds around it. It has 5. How can it do that? Well, remember, phosphorus is a third period element. It can put electrons not only in its s and p orbitals, but also in its d orbitals. And it has up to 5 d orbitals, so it can take quite a few actually. Let's look at an animation of PCl5. So that's a model showing 5 chlorines centered around a central phosphorus atom. The bond angles are not all the same in this case, and we'll talk about that in the next chapter, but PCl5 is a legitimate compound in which phosphorus is a hypervalent atom. Let's draw one more structure. How about this compound? This has the formula POCl3. It's called phosphorus oxychloride. So let's see, that's 5 electrons plus 6 electrons plus 7 times 3 is 21, plus 11 looks like 32 valence electrons. Now in the structure, electronegativities please, 2.1, 3.5, 3.0. Phosphorus is least electronegative, it'll be central. So let's draw phosphorus. 1, 2, 3, 4, 5 valence electrons. 1 pair, 3 singles. Chlorine needs 1 electron to share. There's 1 bond. Here's the second chlorine. That's 2 bonds. Here's the third chlorine. That's 3 bonds. What about the oxygen? Oxygen needs a pair of electrons. You know that oxygen can form a double bond, right? 2 pairs and 2 singles. That's right there. A double bond. POCl3. So number of electrons, let's see, bonding, non-bonding, and valence electrons. Bonding, 1, 2, 3, 4, 5 bonds, that's 10 bonding electrons. 3 chlorines, that's 6 times 3 is 18, and 4 makes 22, for a grand total of 32 valence electrons, and those agree, that's good. So notice that phosphorus has a total of 5 bonds on it. It is hypervalent again. 3rd period, 4th period, 5th period elements, etc. can have more than 4 bonds on the central atom. Page 104, please. Here I've drawn the Lewis symbol of sulfur. It's in group 6A, and it has 6 valence electrons, 2 singles and 2 pairs. And the rules for bonding are that those single electrons will always bond in some fashion. The pairs may or may not. All right, what can sulfur do? If sulfur combines with a reactive nonmetal like potassium, it can take 2 electrons and form a sulfide anion. It could even react with something like 1 potassium and 1 hydrogen, and you could have something like potassium, hydrogen, sulfide, in which one of the bonds is covalent like SH, and the other bond is ionic like in K plus and S minus. What about covalent bonding arrangements? Sulfur can form 2 single bonds, much the same way that oxygen does, to form water. You could have hydrogen sulfide as analogous. Remember, they're both in the same group, 6A. We expect some similarities. What if sulfur formed a double bond, just like oxygen does? Remember, we have oxygen double bond? Well, why not sulfur double bonds? And in fact, sulfur does form S2. It's one of its possible polyatomic forms. Sulfur is using its 2 single unpaired electrons to form bonds, and the non-bonded pairs are still unused. What other possibilities are there? What if sulfur, let me redraw its Lewis symbol here so we can look at it. What if it used its 2 single unpaired electrons to form a double bond, and then used another pair to form another double bond, and then it had an unbonded pair remaining? Can it do that? Sure. It's a 3rd period element. It can be hypervalent. An example is sulfur dioxide, SO2. What if sulfur used, again, 4 of its valence electrons and formed 2 single bonds, and then used a pair to make a double bond, and again it would have 2, 4, 6, 8, 10 electrons in the valence shell. It's hypervalent. An example of such a compound is thionyl chloride. It's called thionyl chloride. It's a nasty chemical. It's very useful in organic chemistry, as you'll see. What if sulfur took 4 of its valence electrons and formed 4 single bonds and left a pair unused? There's such a compound. It's called SF4, sulfur tetrafluoride. Each of these fluorines would have 3 non-bonded pairs of electrons on them. So here's sulfur, hypervalent atom with 10 electrons in the valence shell. What about these other 2 electrons? Maybe they can be involved in bonding too, right? They sure can. What if sulfur used all 6 of its valence electrons, 1, 2, 3, 4, 5, 6, and formed bonds with all of them? What if it forms, say, 2 double bonds and 2 single bonds? What compound uses that? What about sulfuric acid? You've seen that one before. H2SO4. Sulfur has how many electrons in the valence shell? 2, 4, 6, 8, 10, 12. A whopping 6 bonds, but it can do that it can use the d orbitals of the third shell. Again, what if sulfur used all 6 electrons and had 1 double bond and 4 single bonds? Double bond, reserve it for oxygen. These could be fluorines or chlorines. SOF4. Again, 2, 4, 6, 8, 10, 12 electrons in the valence shell of sulfur, 6 bonds. What if sulfur made 6 single bonds, using all 6 of its valence electrons as single bonds? This is SF6, sulfur hexafluoride. It's quite inert. It's used as a dielectric, as an insulator in transformers. And I have read, I haven't tried this, and you can YouTube this and see it, but you know how when you breathe helium, your voice raises up and you sound like a chipmunk. Apparently when you breathe SF6, your voice lowers and you sound like Darth Vader. It sounds kind of cool. Okay, what if sulfur took all 6 of its valence electrons and made 3 double bonds, as in sulfur trioxide? That's an important commercial chemical. So sulfur has great skill and ability. So those are all the possible ways sulfur can form bonds, quite a few. Please take a look at page 105. So I've drawn here Lewis symbols of the 3rd period elements, at least aluminum through chlorine. And then here's an exercise for you to do. Go and take each one of these non-bonded electrons in the Lewis symbol and start bonding them with covalent bonds and see how many possibilities you can come up with, bearing in mind that you can have more than 4 bonds. You could have a lot more. You'll run out of electrons before you run out of space. You could have like pH3, right? Anywhere you have a double bond, put an oxygen or a sulfur in it. Where you have a single bond, you could put a hydrogen or a halogen in it. And these are all possible compounds that can be drawn from these 3rd period elements. We already looked at sulfur's possibilities. Now chlorine has 7 valence electrons, so you could actually have up to 7 bonds around it. Possibly more if it accepted more electrons from somebody else. But just covalent bonds like this, 7 at least. So I ran out of space on this page. Go on the next page. I've drawn here what I believe are all the possible covalent structures for chlorine. So chlorine can have a single bond, monovalent. It could have 3 bonds and be trivalent in a couple of ways. It could have 5 bonds and be pentavalent in these 3 fashions. It could be heptavalent in these options, and maybe you can see another one. So again, these are hypervalent atoms. 3rd period, 4th period, 5th period, they have empty d orbitals. They can form a lot of bonds. Please take a look at page 110. We need to learn what is meant by formal charges and how to calculate them. Page 110. Let's start right over here. So here, this is really important, by the way, so please give it your best. It's really, really important. So I've shown here hydrogen, oxygen, and hydrogen. They're Lewis symbols. Now you know that the Lewis symbol shows only the valence shell electrons, and they represent a neutral atom. So when you see hydrogen with 1 electron, well, that's neutral. When you see an oxygen Lewis symbol that has 6 electrons around it, it's neutral. I know oxygen is element number 8. There are 2 inner electrons. They're in the inner shell. The valence shell electrons are the only things that are shown in a Lewis symbol. So whenever you see an oxygen that has 6 electrons that it owns in the valence shell, it's neutral. Look at a water molecule. Okay. Now we know that oxygen, by sharing it, has a full valence shell. But how many does it actually own? So here's the rule. Listen very carefully. An atom owns whatever it doesn't share. It's not sharing these 4. And it owns half of what it shares. It owns half of what it shares. So half of each bond. This is not oxidation number thinking. It's a different thing. Formal charge is different than oxidation number. If you recall, in oxidation numbers we said let's assign to the more electronegative atom all the electrons it shares. And if we assign all these electrons to it, we say its oxidation numbers -2. But when it comes to structures, line bond structures, we need to be able to write what's called the formal charge. We assign to the atom all the electrons that it doesn't share, These belong solely to oxygen and half of what it shares, so that would be 2 more electrons. So how many electrons does oxygen own here? It owns this many, 6. So we look at the Lewis structure of oxygen and water, we can say, hey, its formal charge is 0. The formal charge of oxygen is 0 because it owns 6 electrons. I know it shares 8, but it owns 6. What about hydrogen? We know that it shares 2 electrons. It has a full valence shell, but how many electrons does it own? Well, it owns half of what it shares, so it owns 1 electron. Each of these hydrogens have a formal charge of 0. I'll put Fc equals 0. Fc equals 0. Likewise, this hydrogen, formal charge equals 0. It's an important concept. Take a look at the left-hand side of the page here. Earlier we drew lithium hydroxide, and so here's sodium hydroxide. It's similar. In sodium hydroxide or lithium hydroxide, there's an ionic bond between the metal and oxygen. So in this structure, how many electrons does oxygen own in the structure? It owns all of what it doesn't share, 6, and half of what it shares. So it actually owns 7 electrons, doesn't it? Now, to be neutral, we know that oxygen would have to own 6 electrons, and therefore in this structure, oxygen has a formal charge of -1. What about the hydrogen? How many electrons does it own? It owns half of what it shares. It doesn't have any unshared. It owns 1. So in this structure, the hydrogen has a formal charge of 0. So notice the hydroxide ion as a whole has a charge of -1. So which of these atoms has that charge? Is it the hydrogen that's -1? Is it the oxygen that's -1? It's the oxygen that has the formal charge of -1 in hydroxide ion. What about sodium cation? What's its formal charge? Well, how many electrons does it own? In the valence shell, it owns none. We're only looking at the valence shell in Lewis symbols. None. To be neutral, it would own 1. It has 1 less than that, so its formal charge is +1. So for an ion like this, a singular ion, the formal charge is the charge. But in a structure, you take the covalent bond electrons and divide them equally among the atoms that are sharing them. Really important. In the appendix on page 248, there's a definition of the Bronsted-Lowry theory of acids and bases, which tells us that a Bronsted acid is defined as a proton donor, and a Bronsted base is a proton acceptor. And so neutralization is simply the transfer of a proton from a proton donor, an acid, to a proton acceptor, a base. Here's an example. In this reaction, hydroxide is a base. It accepts a proton from acetic acid and then becomes water, H2O. At the same time as acetic acid donates the proton, it forms its conjugate base, acetate ion. So you'll notice that conjugate acid-base pairs that are joined by lines differ by a proton. So water is the conjugate acid of hydroxide, and these two species differ by a hydrogen ion. Acetate ion is the conjugate base of acetic acid. They differ by a hydrogen ion. A very important relationship for acids and bases in water is this. The pKa of an acid plus the pKb of its conjugate base is equal to 14, and this is true in aqueous solution. So in the above example, if acetic acid has a pKa of 4.7, it's easy for us to calculate the pKb of its conjugate base. Acetate would have a pKb of simply 14 minus the pKa of the acid gives us 9.3 is the pKb of acetate, its conjugate base. In this table, we have a list of some common acids on the left side and some common bases on the right. And notice that the pKa of the acid on the left plus the pKb of its conjugate base on the right always add to be 14. So for example, the pKa of water, very weak acid, plus the pKb of its conjugate base, hydroxide, strong base, add to be 14. So if I knew the pKa of ammonium ion is 9.2, it would be easy to calculate the pKb of ammonia. I would simply take 14 minus the pKa of the acid and come up with 4.8 for the base. Here's hydrogen fluoride, a moderately strong acid with a pKa of 3.2. So the pKb of fluoride, its conjugate base, would simply be 14 minus 3.2, or 10.8. Notice here that hydronium ion has a pKa of negative 1.74, it's a strong acid, and its conjugate base, water, has a pKb of 14 minus a minus 1.74, or plus 15.74. So water is as strong a base as it is an acid, which is why it's completely neutral. It's a very useful relationship in chemistry. Page 111, coordinate covalent bonds and mechanisms. This is the most important thing in the course and for the rest of your life at college. Okay, you really need to get a hold of this and you'll get organic chemistry. So give it your best here. Take a look at the reaction. If you take water and it combines with a hydrogen ion, I'll bet you know what this forms. But how does that reaction actually work? How does that form? Let's take a look. We'll draw the Lewis structures and we'll start to understand how. So here's a molecule of water. Oxygen has 2 single bonds and 2 non-bonded pairs of electrons. Here's the H+, it has no electrons. We previously described Bronsted acids as proton donors and Bronsted bases as proton acceptors, but also we describe acids and bases as being Lewis acids or Lewis bases. A base is still a base by either system, but it's a different definition, a different way of thinking about it. Okay, so a Lewis base is defined as being an electron pair donor. And Lewis acid is an electron pair acceptor. So take a look at the mechanism for this reaction. When this Lewis base, water, bonds with hydrogen ion, it does so by donating or using its pair of electrons to form a bond to the H+. I'll say that in a minute again, but let's show the structure of the product. It will look like this. So nothing's changed here except this has happened. So let me color it in here a bit. I'm going to say that this pair of electrons, I'll color them green here, was used to form a bond to this hydrogen ion, which is no longer an ion, it's now neutral. Now this is hydronium ion, right? H3O+. In hydronium ion, what are the formal charges of each atom? What about the oxygen? How many does it own? It owns what it doesn't share, and half of what it shares. It owns 1, 2, 3, 4, 5. It only owns 5 electrons. Remember, for oxygen to be neutral, oxygen has to own 6 electrons to be neutral. Since it only owns 5, it's positively charged. The positive charge here, H3O+, is actually on the oxygen. And a positively charged oxygen is called an oxonium ion. Oxonium cation, if you wish. The IUM ending reminds us of a cation, like ammonium ion. Can oxygen actually be a cation? I thought it was just an anion, like oxide. Well, sure, it can be oxide, an anion, but when it's a cation, it's oxonium cation. So within the hydronium molecule, it's actually the oxygen that has the positive charge. Now back to our mechanism. It was the water molecule that used a pair of electrons to form the bond to the hydrogen. This type of bond, when one atom provides both electrons to form the bond, is called a dative bond. And that's listed on the previous page, but I'll just write it here again. This is a dative bond. It's kind of like going on a date, and actually the Latin implies that. Dative means giving. So the one atom provides both. So say like you're going to go to an event with a friend. Maybe it's a hockey game, a baseball game, maybe it's a concert or something. And if you decide you're going to buy both tickets to go to the game, it's like going on a date, then you go with your friend to the game. But then you share the tickets, right? So you go together. So in this reaction, the oxygen in water is a Lewis base. It is an electron pair donor. Remember, water can be amphoteric, right? It can act as an acid or a base. If it's reacting with an acid, then water acts as a base. If water was reacting with a base, it would react as an acid, and we'll see that. But right now, water is reacting with an acid, so it's acting as a base. It's a Bronsted base because it's a proton acceptor. It's a Lewis base because it's donating a pair of electrons. Let me show you what this is not. Sometimes students will draw this. And they'll draw the arrow this way. They'll think hydrogen's coming over here and forming a bond to here, and that's the product. That is incorrect. In these arrows that we show, a half arrowhead or fish hook is a 1 electron transfer. A full arrowhead means a 2 electron transfer. And that's what I'm showing here. There's a 2 electron transfer from the oxygen to the hydrogen. Now, this arrow drawn from hydrogen ion is saying hydrogen ion is donating a pair of electrons to form a bond. Well, it can't. Hydrogen ion doesn't have any electrons to donate. It can't buy any tickets. It's broke. So this is wrong. And often students are thinking that hydrogen ion comes over here and bonds with it. Well, yes and no. Remember, in a beaker of water, there's a bajillion hydrogen ions, and there's a bajillion water molecules, and everyone's going back and forth and up and down and every which way. We can't really describe the motion of the molecules or ions. All we can describe is the motion of the electrons, and that always happens from the base to the acid, from the donor to the acceptor. Okay, so it's really important you get your arrows right from the beginning. Try and think of that. Who is donating and who is receiving? If you like football, think of the electron donor as being the quarterback, and he's throwing the football. And then the receiver is the Bronsted acid, the Lewis acid, the electron acceptor. If you like hockey, think of the person who's passing the puck as the donor, and the person who receives the puck is the acceptor, whichever way you want to think of it, but always put the arrow from the donor to the acceptor, from the base to the acid. And this is going to be true in organic chemistry. Virtually all reactions in organic chemistry work in this fashion. So the sooner you get a hold of it, the happier your life will be. This is how we show reaction mechanisms, is by the transfer of electrons. I got no space here. Here's a reaction mechanism. Shows the transfer of electrons from the base to the acid. Let's try another one. Let's say we take ammonia, and ammonia is a base. When you put it in water, what does it make? What do bases make in water? They make hydroxide ions. So let's draw that. Here's ammonia. We put it in water. If you do that, you'll check the pH of the solution. pH increases. It must be forming a hydroxide ion. Here is hydroxide ion. So that means the water must have lost a hydrogen ion. Where do you suppose it goes? It goes to the base, the ammonia, forms NH4+. Wow. So in this reaction, ammonia is the base, and water is the acid. All right, let's draw the Lewis structures, and then we can draw the mechanism. So here's ammonia. Here's water. All right. So in order for oxygen to become an anion, it must gain an electron. notice that the ammonia picks up an H+. So here's the mechanism. Our base, our Lewis base, is an electron pair donor. It's this pair of electrons that forms a bond with the hydrogen in the water. Now, hydrogen can only form one bond at a time. It can't be bonded to both oxygen and nitrogen at the same time. That means this pair of electrons has to come over here and stay with the oxygen. That gives us the structure. The nitrogen now has an additional bond to an additional hydrogen, and the oxygen is no longer bonded to the hydrogen. Now what about these charges? So when nitrogen uses this green pair of electrons to form this new green bond, it's actually lost, if you will, one electron. How many electrons does nitrogen actually own in the structure? It owns half of what it shares, 1, 2, 3, 4. So this is a nitronium cation. So within the ammonium cation, this is ammonium ion, there's a nitronium cation. Note that oxygen now owns a pair of electrons that formerly it only shared. So let me color, let's see, how about we'll make this bond here blue, okay? And now this becomes a new pair of non-bonded electrons on the hydroxide ion. Now what's the charge on the oxygen in here? How many electrons does it own? 2, 4, 6, and 1 is 7. It actually has a charge of -1. So this is another acid-base mechanism. The base, the Lewis base, is an electron pair donor to one of the hydrogens of the water. And then hydrogen can only have one bond at a time, so then the bonded pair between oxygen and hydrogen becomes a non-bonded pair. We drew earlier BH3, or at least we talked about it, and we're going to react at this time with sodium hydride. Believe it or not, this will be an acid-base reaction. Now BH3, boron is in group 3A, so it has 3 valence electrons. It's going to form 3 single bonds. Sodium hydride, the difference in electronegativity isn't all that high, 2.1 for hydrogen, minus 1.0 for sodium. If you looked on a scale, it would tell you it's polar covalent. But if you recall from the study of chapter 1, the alkali metal hydrides are actually ionic. So the delta En doesn't work all the time. It's simple, but it doesn't always work. In sodium hydride, you actually have a full separation of charge. Okay, so sodium hydride is a really powerful base. It's way stronger than sodium hydroxide. The sodium hydroxide, little digression here, hydroxide is a pKb of minus 1.74. Hydride, pKb, is negative 21. So those are powers of 10 difference. It's like 10 to the 19 times stronger a base. It's a really strong base. Now BH3 doesn't look like an acid per se. It doesn't really donate any hydrogen ions, but it is an electron pair acceptor. It's a Lewis acid. Now why would it accept a pair of electrons? How many electrons are in the valence shell? Only 6. It only has 3 bonds. It's got an empty orbital, and that makes it a good candidate to accept a pair of electrons. So we could draw a reaction, we could draw an acid-base mechanism from our electron donor, wonder what that's going to be, really strong base, to our electron acceptor. What's that going to be? Well, the boron atom has the empty orbital to accept the electrons. And so now we have boron with its original 3 hydrogen atoms, but it's also, and let me color these green, this pair of electrons is being donated to form a bond to the new hydride, which joins the club, BH4. And the sodium ion is just a spectator ion, isn't it? So it's just going to be sodium ion. Now, what's missing from this? What's the charge on the boron? Boron is a group 3A element. It's neutral when it owns 3 electrons, but now it owns how many? 4. So boron is actually boride. It's a boride anion. And you know what? This whole anion altogether is called hydroboride. Okay, this is an acid-base mechanism. It's probably one you wouldn't recognize, but if you understand electron transfers, it makes some sense. So this seems like a good place to stop this lesson. I've introduced a lot to you in this lesson. I've introduced the idea of reaction mechanisms, electron donors and electron acceptors, Lewis acids and Lewis bases, formal charge of atoms, conjugate acid-base pairs. We'll be doing this again and again now as we do many more acid-base mechanisms. We'll draw structures and draw mechanisms, so this will come together over time. So don't give up if you're having difficulty at this point. Stay with it. We'll do many more examples and this will start to come together. It typically takes some time to get a hold of acid-base mechanisms. This is probably the most difficult part of the course, and it's probably the most important and useful part of the course. You will use this to understand chemistry in all of the organic courses upcoming, and there are 5 of them, as well as analytical. It'll help you as well. So don't give up at this point. Stay with it. It will get easier. We'll do many more examples in the next lesson.